Everything that we're used to seeing and touching is made of matter. Electrons, neutrons, and protons make up atoms, which make up molecules, and so on. But it turns out that for every matter particle in the universe, it's possible to create an opposite particle. A particle with almost all of the same properties as the matter particle, except with opposite charge. These are called antimatter particles, and when matter and antimatter come in contact, they annihilate in a burst of energy, so there's really not much antimatter out there today. And yet, physicists were able to predict the existence of antimatter years before we ever saw it in experiment. So today we're going to talk about how physicists get to such an odd prediction, and what antimatter really tells us about our universe. You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. My name is Shalma, and I'm a PhD student at NYU, and my co-host is Dan Hooper, theoretical physicist at Fermilab and the University of Chicago. So to really understand how physicists ended up predicting antimatter, we have to go back to 1905, when Einstein first wrote his theory of special relativity. So we won't go into it in too much detail, just because it could really take up a whole episode on its own, but basically, Einstein's theory said that for objects moving close to the speed of light, physics gets really different. And that's because the speed of light is something of a cosmic speed limit. Any particle with mass can't travel at or above the speed of light. So any theories that physicists write for slow-moving particles have to be totally readjusted in order to account for particles moving at relativistic speeds, or speeds close to the speed of light. And so, in 1925, when Erwin Schrödinger revolutionized quantum mechanics by writing down what we now call the Schrödinger equation, that's exactly what physicists wanted to do next. They wanted to be able to upgrade Schrödinger's equation to explain particles moving at relativistic speeds. But before we talk about how physicists did that, let's talk a little more about Schrödinger's equation. This equation is basically all I studied when I took quantum mechanics as an undergrad, and it's really important in describing quantum systems.
Yeah, I would say it does two things. It describes how a quantum system changes or evolves, but it also tells you what the possibilities are for a quantum system. So, like if I apply the Schrödinger equation to a hydrogen atom, you solve that and it gives you a list of states that all those electrons can be in. And it can't be in anything else. It can be in those or some combination of those very specific solutions to that equation.
So Schrödinger's equation is really successful at describing systems like a hydrogen atom or a particle in a box, but there are limitations to when you can use it. And that's because it really isn't compatible with Einstein's theory of special relativity.
Yeah, the Schrödinger equation is built from a Newtonian idea of space and time, and it breaks down if you start including the effects of relativity. So, they knew very shortly after Erwin Schrödinger wrote down that equation that this might be a good approximation that you can use for slow-moving things, but it can't possibly be the whole story. There has to be something else that would replace it or expand upon it that would describe fast-moving objects.
So for the years following the Schrödinger equation, lots of people tried to figure out how to do this, how to make the Schrödinger equation work for relativistic particles. And it took a fresh pair of eyes to really do it.
The person who finally solved this problem was a young physicist named Paul Dirac. So I kind of, look up to him as sort of a superhuman mathematical physicist. He had this almost religious reverence for mathematical beauty, and he talked about this in kind of interesting poetic terms. And he also had a really hard time with things people would say that weren't meant to be taken literally. He seems to have only been able to understand language when literal. A story that was told in a biography of his I read is that he had made arrangements with some journalists to come to his house and interview him. And when the journalists arrived, Dirac was out in his garden, tending to his garden. And the journalists looked at him. He didn't know what Paul Dirac looked like. So he said, he thought maybe this guy was the gardener. And he said, "Excuse me, is Professor Dirac in his house?" And he said, "No." And the journalist left. And it never occurred to Paul Dirac that was not what the guy meant, or that there could be a different way to interpret that sentence. So anyway, he was something of an odd duck, but an absolutely brilliant mind.
So Dirac was able to combine special relativity with quantum mechanics to come up with his equation that we now call the Dirac Equation. And how he did it was by following a pretty similar line of reasoning to what Schrödinger did when he wrote his original Schrödinger equation.
So like the kind of the first step you would do of trying to work out the Schrödinger equation is you would write an equation which says like the total energy looks like the kinetic energy plus the potential energy, and then you treat everything like a wave and blah, 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 and you get the Schrödinger equation out. Dirac did something similar, but incorporating the ideas of energy that are in special relativity, and that turns out to lead you down a very different road, giving you a very different equation and very different results of that equation.
And these new results from the Dirac equation aren't just different than the Schrödinger equation results. They imply something totally new about the nature of matter.
With the Schrödinger equation, if you, like, let's just say you take a part, like some particle confined to some space, something a physicist would call a particle in a box. The Schrödinger equation will give you a list of states that those electrons can be in, and all those states are have a positive energy associated with the electron. So that makes sense. Negative energies don't have a lot of meaning in most cases, and that's what your intuition says should be the case. But when you do the same thing with the Dirac equation, you find that there are all these positive energy states. And then on the other side of zero, there's a bunch of negative energy states that an electron can be in. So this is instantly problematic.
An electron always wants to be in the lowest energy state possible. Think of holding a ball at the top of a hill. That ball wants to be at the bottom of the hill, and as soon as you let it go, it will. So if there are suddenly negative energy states available to electrons, those electrons will go there, and in particular, they'll go to negative infinity.
As it does that, it will just release more and more energy in the form of light or other radiation, and that electron will produce an infinite amount of energy, and obviously that's not what's going on, so like that can't be the answer. And Dirac instantly knew that. But he had a solution and an idea that how you could deal with this. He basically said that all those negative energy states might already be filled. So what he had in mind is like the natural state of the vacuum. The state that we describe as empty space is one in which all of those negative energy states already have things you can think of as particles occupying them. And since they're already full, you can't put a new particle in there. That's what we call the Pauli exclusion principle, something you people see in chemistry classes. And that means that just like with the Schrödinger equation, that electron can't fall all the way down to negative infinity. It has to stop at the lowest positive energy state.
So Dirac answered the problem of negative energy states by supposing that the states are already filled, just with particles that already exist in the vacuum of space. But this leads to yet another idea.
So Dirac then imagined that something like a photon might come along and it might hit one of those particles in a negative energy state, popping it out of its negative energy state and moving it up into a positive energy state. So what just happened? When that happened, you suddenly created an electron that wasn't there before with a positive energy, and you've created a hole in the vacuum. That vacuum used to be electrically neutral, but now it has one less negative charge in it, which is the equivalent of saying it has one more positive charge in it. So that photon came along and it created an electron, and it created something just like an electron with a positive charge.
What physicists would say today is that photon created an electron-positron pair, an electron and an antimatter electron we call the positron. So that's how Dirac got from negative energy states in his Dirac equation to the prediction of antimatter, particles that are like normal matter but with the opposite charge. And it's not just electrons. Every particle has an antimatter partner. Quarks, which are the fundamental particles that are the building blocks of protons and neutrons, have antiquarks, which carry the opposite quantities of both electric charge and another kind of charge that particle physicists call color. And the same goes for other particles. In fact, any particle you can imagine. The only exception are particles like the photon, the particle of light. Since the photon has no charge, its antimatter partner is actually just an identical photon. So a photon and an antiphoton are the same thing. But not only are antimatter particles possible, they're actually created every time we create normal matter.
Roughly speaking, what Dirac's equation was telling him is that you could take energy and use that energy to create matter along with antimatter in equal and opposite parts. And furthermore, his equation was saying that in order for things like electrons to be allowed to exist, there had to exist or be allowed to exist those antimatter versions of the same particles with the same mass, but opposite charge and other properties.
So to create antimatter, you have to make it in a pair with normal matter. For example, for an electron and a positron. To create an electron-positron pair, you need to have two photons collide that have a large enough energy to make up for the masses of the electron and the positron. And that's going to cost you over 1 million electron volts of energy.
In the 1920s, that was a lot of energy, but like it is really nothing. I mean, compared to modern machines, like the Large Hadron Collider is colliding protons together with 13 trillion electron volts. So this is, wildly smaller than that. The Large Hadron Collider produces tons of antimatter all the time. I say that, but really in the entire life of Large Hadron Collider, it's made something like a nanogram of antimatter, but like a lot of particles still.
The particle accelerator that has created the most antimatter is called the Tevatron. And up to a few years ago, it was operating at Fermilab, right outside of Chicago. Over the course of its operation, the Tevatron produced about 15 nanograms of antimatter. That might not sound like very much, but it's 10 to the 16 antiprotons, which is quite a large number of something that's so rare in the universe. And if you're worried now about those 15 nanograms of antimatter causing a huge explosion right out of Chicago, you don't have much to worry about.
If you took all of the antimatter that all of the scientists have ever made in the history of the Earth and annihilated it all at once, it would still, it wouldn't be dangerous. I don't think I could make a cup of coffee with it.
So physicists can create antimatter at big experiments like the Large Hadron Collider in Switzerland, but they're also produced naturally and come to us in the form of cosmic rays.
Particles from space that we call cosmic rays hit the atmosphere all the time. And some of those have enough energy to create things like electrons and positrons in pairs. And they probably do it in slightly more complicated ways, like producing things called mesons, which decay to things like this. But all the same, you make antimatter in these cosmic ray collisions all the time. And in 1932, so just shortly after Dirac predicted the existence of the positron, an American physicist named Carl Anderson, who was studying cosmic rays, started to measure things that looked like electrons, but with opposite charge. He used a tool called a cloud chamber, which kind of tracks the route of an energetic particle. And he put a magnetic field around it. So, electrons would curve one way in the magnetic field. And he was seeing things that had the same sort of characteristics as an electron, but were curving the other way. We now know that he was observing positrons for the first time, just shortly after Dirac had said these things had to exist.
And after the discovery of the positron in 1932, physicists started to see other antimatter partners showing up in experiments. In 1955, we discovered the antiproton, and in 1956, the antineutron. Since then, we've discovered antimatter versions of every single kind of matter that we know. In the 1990s, physicists were even able to create complete anti-atoms for the first time. And in theory, with a big enough experiment, you could produce anti-anything. Anti-planets, anti-stars, anti-galaxies. So that's all for this episode. But there's a really big caveat to all of this antimatter stuff that we haven't really mentioned. Now we know that we actually can't create matter without also creating an equal amount of antimatter. But if that's true, and we look around and we see in our universe all matter everywhere, we don't really see any antimatter day to day, we have to ask, why is there so much more matter in this universe than antimatter? And we'll answer that question next time on Why This Universe. This episode was produced and edited by me, Shalma Wegsman. Research and writing is done by Dan Hooper and I. Dan is a theoretical physicist at Fermilab and the University of Chicago, and is the author of many books, including most recently, At the Edge of Time, Exploring the Mysteries of Our Universe's First Seconds. All music in Why This Universe is produced by Jake Kleinbaum. Thank you so much for your support and for listening, and we hope you tune in next time to Why This Universe.